So if in this instance here, let's kind of make an example out of the heating pad. Let's say you had 20 ohm resistor, 20 ohm resistor, 20 ohm resistor. Okay. Let's say I ask a question like this. Let's say I want to make, when I engage, let's say I want to make the hottest setting of that heating pad. Let's say I want to make the hottest setting twice as hot. So I don't want it to be 3 times as hot. So let's say I want to make the hottest setting twice as hot as the lowest setting. Then what should R be? So I'm kind of relating it back to the heating pad question. So let's say I want to make the hottest setting twice as hot as the lowest setting. What should R be? So that could be question 1. And then B, how hot is the middle setting going to be? How hot is the middle setting? Middle setting. Okay, so when you have the hottest setting, that means you're engaging all of them, right? So then this acts as like this. R 20/3, right? That's the hottest setting. The 3 resistors in parallel act as 20/3. So then what's the net resistance here? Then this is in series with all 3 of them, you see? So then the total resistance is going to be what? R plus 20/R, right? So then how together all 3 of these, how much power are they going to dissipate? Because this is the heating pad. Because these 3 wires go inside of the heating pad, but not the resistor. The resistor is just an external. You see that? So my question is, how hot do these 3 get? So if you know the total resistance is this plus this, then it acts like this. This is the R total. So then the current is going to be, the current in the circuit is going to be the voltage of the source divided by R total. Oh no, R. You know what, I'm running out of room. Oh, let's see here. Let me get it. I like this problem, kind of the realistic everyday problem again. So then we have here the current is V over R plus 20R. Then you're going to go back to the previous circuit, R 20/R. Then you're going to argue that the current here, same things kind of when we did for the capacitor, right? We're going to argue that the current that was in here is the same as the current that is in these 2 resistors because they're in series. right? So these two have the same current. So they have same current. Then what's the power lost just in that portion? If I know the current going through that, and I know its resistance is 20/3, that's all I need. So I don't really need to calculate the voltage of this. In this case, if I know the current is that, right? If I know that the current is that, then I could use this equation, P is equal to I squared R. So remember, there's three forms of the power equation. Where was it? Well, I wrote it earlier. And depending on if you know the current going through that resistor, you could just directly use that instead of the voltage if you don't need the voltage. So then you can say the power lost in the three resistors, the three wires, is going to be this thing, the current squared, V over R plus 20/3 squared times the resistance R, which is 20/3. Right? So now I want this power to be twice the power as the lowest setting. So in the lowest setting, what's the resistance of the three wires? Lowest setting what's the resistance of the three wires? Just 20, right? So then what would the net resistance be in that case if it's just 20? So then it'd be R total would be R plus 20. And then we can go through the same arguments. The current would be V over R plus 20. All right, then the current here will be the same as that guy. I, right? V plus R20. And then you're going to say the power lost in here in the one wire is going to be what? The current squared over R times R again. So then it's going to be this current squared, R plus 20, squared times what? Times the resistance, which is 20. And then you want this to be twice that. So we're solving for what R should be. So in other words, you're limiting how hot that thing can get because you don't want somebody to put it on the hottest setting and then say, oh my gosh, it's 3 times hotter, right? Because if R is 0, the hottest setting will be about 3 times hotter than the coldest setting, the lowest setting. 3 times hotter might be too much for the average person, and they might sue the company, you know. So that's why you're putting an external resistor to control that. So you want the hottest setting to be twice this. So then the condition is that you want this guy to be twice of this guy. And then the V's cancel. And the 20s cancel. And you could cross multiply. So you could get R plus 20 squared is equal to, cross multiply this one over there. And then the 3 cross multiply over there. So that's 6. Right? 3 times 2 is 6, and then this one cross multiply over there. R plus 20/3 squared. Oh, okay, became a nice problem. Now square root it. R plus 20 is equal to square root of 6. R plus 20 over 3. When I do that, there might be a second option, right? Plus or minus, but I'm not sure if the minus is going to give me a positive answer. But you know what? We might as well write it. Plus negative 3.67. No, I'm okay. Then just do two negatives cancel. So invert this times 3.67 negative. Okay, R should be 2.53 ohms. Is there another answer, another possibility if I use the negative? So R plus 20, negative square root of 6R, negative square root of 6 times 20 over R. Then you're going to have R plus the square root of 6R, and then 20, right, this one goes over here, R plus square root of 6R, this one goes over here, negative 20. Oh no, this gives you negative. Yeah, this gives you negative. Okay, forget the negative option then. Yeah. Okay, 2.53 ohms. Let's see. What was the resistor there? Blue, red, orange. It's a 3 and the gold. So it's the gold one is the error. I think I see it. Is that green or blue? Hard to tell. Remember the code that we learned yesterday? Blue, red, orange. Blue, red, orange. So now we know how to read it, right, guys, everyone? Okay, so blue is a 6. Red is a 2. So 62. 62. And orange is the power of the 10. Oh, that's actually big. 62 kilo ohms. Huge. 62 kilo ohms. So you just do it like this, right? Blue was 6, red was 2, and then this is the power of the 10, 10 to the third. So 62 times 10 to the third, 62 kilo ohms. So it's much bigger than what we calculated. Nice stuff, huh?
Yeah, it's easier than last week's, I think.
Oh, in terms of which one? The capacitors?
Yeah, I had trouble with those.
Oh, okay, yeah, you're right. Okay, so now we can kind of see this was a good example of a parallel, kind of like a parallel series circuit. Let's see here. We can do one actually on the FED Colorado, make an example from there.